So now we're gonna talk about a very new reaction which is known as SN2 reaction, which is also known as a bimolecular second order nucleophilic substitution reaction. Biomolecular second order nucleophilic substitution reaction. What happens in this case? A nucleophile react with RL alkyl halide in the presence of solvent. It forms RNU plus L negative. So what happens? RL actually has a polarity delta positive and delta negative. So nucleophile attacks and it forms a transition state. Nu, then R, then L. This is a transition state. And further forms Nu R plus L negative. Now and that Nu negative, what happens? It attacks on the back side of this X, Y, and this is Z. So it attacks on the back side of this compound, and when it attacks on the back side of this compound, it living groups lives from the further side. And it is similar to the concept like we have an umbrella. Umbrella, when there is a wind flowing, an umbrella inverts. The umbrella inverts, right? Similarly, this compound inverts. The intermediate step is state is C, Y, Z. Then we have Nu. Then we have L, living group. This is our intermediate step. So now this nucleophile is keeping on attacking and living group is keeping on living. So it forms Nu, C, X, Y, and Z, and it forms L minus. So it has been inverted like umbrella is inverted when the wind is flowing. Similarly, this nucleophile is attacking over here and it is leaving. So now it has left and this all bonds invert flips. So this we give a name. It is known as inversion. It is known as inversion on or Walden inversion. Inversion or Walden inversion. This is also known as inversion or Walden inversion. What are the characteristics of this reaction? Characteristics of reaction. First of all, it is a single step reaction, nothing like SN1, which was a double step reaction. It is a single step reaction. Second, rate equals to K times RL and Nu minus. The rate determining step is also that one. Third, order of the reaction is 2. Fourth, it is a SN2 reaction. Fifth, rate is inversely proportional to the bulkiness of XYZ. How bulky the groups are, the reaction is inversely proportional to that. More the bulky will be the group, more lesser will be the rate of the SN2 reaction. Right. Sixth, rate again similar to the SN1. It is stability of transition state. Stability of transition state. How do we define the stability of transition state? Let's do some problem regarding that. Like we have CH3 example, then CH3, CH2L, then CH3, CH and CH2L, then CH3, C, CH3 and CH3 and L. So when we go left to right, the rate decreases. Why rate is decreasing? Because it is a bulky groups are attached over here. Bulky groups are attached, and here less bulk, the bulkiness is less. to the living group, directed is to the carbon, and this the first one is a very less bulky. So that's how we see. Seventh, we have no rearrangement, no carbocation. There is a no carbocation formation, hence there is no rearrangement. No carbocation means no rearrangement, and eighth is rate is directly proportional to the living group ability. Inversely proportional to the basic strength of L negative. So we have RF, RCl, RBr, and RI. HI is a strong base, so I negative is the best living group among these four. So this is the order of the SN2 reaction. So that's the order of SN2 reaction. Ninth, a nucleophilicity. We have seen the nucleophilicity. Ninth point, nucleophilicity. Nucleophilicity Nu minus when react with Rl, it will form Nu R and L, and it will form NuR plus L negative. So rate is directly proportional to the strength of the nucleophile, unlike the SN1 reaction. Nucleophile SN1 reaction, right? Like we have an example CH3O minus react with CH3Cl. This is a SN2 mechanism. And B as PHO minus react with CH3Cl, and it forms SN2 reaction. We know that the strength of the nucleophile is greater in A, so the rate of the reaction will be more in A. So rate wise, A will be more because PHO minus is greater than PHO as stability because it is involving in resonance. PHO minus is involving in negative charge is involving in resonance. So PHO minus is involving in resonance, so it is a greater stability. Tenth last point of this characteristic, not last point, the next point of this characteristic is solvent favorable. Which solvent is favorable for SN2? Is polar aprotic. Why polar aprotic? We have seen polar aprotic dissolve only cation, not anion. So only solvate cation. It only solvate cation. So intensify nucleophile. Intensity of nucleophile retains, doesn't decreases. Intensity intensity of nucleophile remains and it doesn't decreases. So intensity of nucleophile doesn't decreases over here, like we have SH negative in presence of CH3Cl, and we have water. So water only solvent in form CH3SH. B, we have SH minus in CH3Cl in presence of dimethyl sulfur oxide. It will form CH3SH. So where rate will be more, we know that H2 surrounds SH also. H2 surrounds SH also, but DMSO doesn't surround SH. So rate in second case will be more. Now we're gonna talk about the stereochemistry of the reaction. We're gonna talk about the stereochemistry of the reaction. Stereochemistry of reaction. Like we have a compound, a Newman projection is given here, Cl, CH3, H, D, CH3, and H. We have OH minus 1 equivalent, and we know reaction is SN2. So the product form will be, here will be D, here CH3, and here we have H. Then OH will go here then CH3 will go here, then H will go here. So how does this reaction is happening? How does this reaction is going to take place? If we look at the reaction, we have let's Saur's projection. Draw the Saur's projection. B R H and D, and SH minus attacks. So SH minus will replace the BR minus, right? So it will form a CH3 H D. It will form a line. That's how it will form a line. And here will be hydrogen and deuterium and SH. So that's how it will invert. Now, if we see, we have seen the Newman projection, Source projection. Let's see one example in Fisher projection. CH3 DH HCl and D. We are taking RS minus. Then it will gonna replace this chlorine, but with the inverted configuration. So one compound will change, one compound will be inverted. It will form RS, then H, then D. So that's how we see the we have seen on all the three projections. How do we see in wedge dash? It is very simple, but we are seeing in other projections. Now we have to compare the rate of SN1 reaction. We are solving some problems. Compare rate of SN1. We have some SN1, then we're gonna compare the SN2 also. First we have chlorine, iodine. We know iodine is a good living group. Second, we have Cl, then CH2Cl. So CH2Cl is a carbocation is stable. Third, we have chlorine over here, chlorine over here. Then this, if we talk about the SN1, if we talk about the SN1, we are comparing SN2 actually here. That's comparing SN2. So we will see bulkiness. Okay, and fourth, iodine. Iodine. We are comparing bulkiness, iodine over here. Fifth, Br, then it is Br. SH minus 1 equivalent. And we have here a group attached methyl. So it will be Br and SH will attack on the back side and the below side because it is less bulky group. Let's solve some more problem. Sixth problem. Br CH2 CH double bond CH Br OH minus 1 equivalent. So we know that this Br here the it is not a good living group, it is a good living group. So it will attack HO CH2 CH2 CH double bond CH and Br. Let's talk about this seventh. Br we have and chlorine. It will react with OH minus then 1 equivalent. So how it will react? OH chlorine. Bromine is a good living group, and that's how this reaction will gonna take place. Bromine, then CH2Cl. It will react with SH minus, which is 1 equivalent. So which will go? Cl will go because Cl is attached with the carbon. Oh, okay. It is Br. CH2SH. Because that is the only possibility to break the bond because sp2 hybridized is not break easily, and it is also resonance stabilized with the bromine lone pair. Now we're gonna compare the rate of SN2. Compare rate of SN2 between two reactions we have. A. First, CH3Cl plus CH3 CH2OH. Second, CH3Cl plus CH3 CH2O negative. We know the second reaction more is fast because it is a the strength of nucleophile is more. In case of SN2, we have to consider the strength of nucleophile also. CH3Br plus O negative in react with water. Second, CH3Br it react with S negative. So in presence of water. So we know in second we have greater strength of nucleophile. O minus is less nucleophile than S minus. That nucleophilicity and basicity we have seen already. In C we have CH3Br plus CH3O negative, which is 1 molar. And second we have CH3Br and we have CH3O negative, which is 2 molar. We know that the rate of SN2 depends on the concentration of nucleophiles. So second is the answer. D we have first CH3Cl, which is pH3n in presence of water. Second we have CH3Cl in presence of pH3p in presence of water. So we know phosphorus is a greater nucleophile because nitrogen has more electronegativity, and because of more electronegativity it has more tendency to hold the electron. So answer is second. Seventh we see. Now continuing the questions. Next question E. HCl. Now we are going to solve some problems. HBr. So OH minus 1 equivalent is attacking. We know the reaction is SN2. And we know that the bromine is a good leaving group. So we will be removing the bromine. So hydrogen, chlorine, then OH, then H. Eighth we have Cl, CH2, C, CH3, CH3, then CH2, CH2 and Cl. So I minus, which is 1 equivalent. So where it gonna react? It is the SN2 reaction, but the bulkiness on the right hand side is less and left hand side chlorine is more. So right hand side chlorine will shift, will move CH3 and CH2, CH2, then I. The next question, G question, Cl, CH3, D and H. So when we react with SH negative, it will form H, SH, H and D. Okay, it will replace the chlorine. It will replace the chlorine, but with the inverted H, CH3, H, H, D, D and Cl. It's gonna react with SH minus. So it will replace chlorine, but with inverted configuration. It will we gonna exchange any one. How we inverted the configuration in Fischer projection? We exchange that chlorine with hydrogen or deuterium with hydrogen. We exchange this, so we have changed the configuration, inverted the configuration. I we see if we react that CH3 with Cl. So when we react, it will react with OH minus and it will form CH3 and OH will obviously gonna replace chlorine. Now, how do we draw the energy diagram for SN1 and SN2? Energy profile for SN1 and SN2. Sorry, SN2. We have seen for SN1. So RL will react with nucleophile. It will form RNU. R then L. Then it will form NUR plus L negative. And here CH3Br example will react with OH minus, it will form OH will replace CH3 will replace Br, and it will form CH3OH plus Br negative. So how does the energy diagram we represents? If we try to draw its energy profile diagram, here we have a y-axis, here we have a x-axis, here energy, and here reaction coordinate. So initially it was CH3Br plus OH minus, and it will form CH3OH plus Br minus. And reaction is exothermic, and we have intermediate transition state, so it is a single step reaction. So only one transition state we will be seeing, TS. Okay, which transition state? Where OH was replacing C with forming Br, and all these three molecules were in the same plane. H, and H were in the same plane. These three H are in same plane, right? So this is reaction coordinate. This is the diagram we see.